Hi kiddos, welcome to Unit 7, which is a pretty short unit. It's not going to take us a lot of time to get through this content, and it's a unit that's going to teach you or go through the basics of differential equations, which when you move on in your math courses is an entire course. Differential equations is an entire course, sometimes two, and it's fun. It's one of my favorite courses, so this will be fun too. We're not going to spend a lot of time on word problems today, but I do just kind of want to show you where we're going. So first off, a differential equation is simply an equation, so you have to have an equal sign in it, that contains a derivative. So you have a derivative inside your equation. This is going to kind of feel similar to things we've already done. Maybe not all the way, but it shouldn't be completely mind-boggling. So if we read, suppose you fill a tall cylindrical can with water and punch out a hole near the bottom. Water leaks out quickly at first, then more slowly as the depth of the water decreases. The rate at which the height of the water in the can changes is directly proportional to the square root of its height. So I tried to emphasize some key words here. The word rate. I know we've been taking integrals for months, but derivatives are a thing too. And the word rate means derivatives. So the derivative of what? If I read more, the rate at which the height leaks. So this would be the derivative of the height with respect to time. I'm assuming it's time because as time moves on, the water leaks out quickly and then slowly. So it's over time. All right, the rate at which the height of the water of the can changes is, there's your equal sign to make it a differential equation. It's already a differential equation, friends, because you have a derivative and you have an equal sign. Directly proportional, I'm gonna skip over for a second and let's read the rest of it. So directly proportional to the square root of its height. So square root of h. Okay, that's what this equation, this differential equation looks like when all I do is take the words and translate the words into symbols. This directly proportional is some constant of proportionality that almost all of your differential equations will have. It's called constant of proportionality, and I feel like you may have encountered this before when you did like exponential growth and decay, maybe with Pickle or maybe in Algebra 2. But that's a differential equation. So we will do lots of word problems with these, but we're going to spend today talking about a specific kind. We're going to talk about separable Diff Eqs. So there's lots of kinds of differential equations, like tons, and that's why there are courses devoted entirely to differential equations. We are only going to deal with separable differential equations because we are only going to solve separable differential equations. So what it means to separate means that you are able to get your x's with dx and you're able to get your y's with dy. So let me show you an example of a separable differential equation. So here's a derivative. That's separable. This one's not. I cannot separate this differential equation because I cannot rearrange it in such a way that I have x over here with dx and y over here with dy. I can't force that manipulation. I can't force that algebra. So that one is not separable. Okay, let's work one. There are two steps here for solving a separable differential equation. Step one is to separate. And this is pure algebra. You are just manipulating things around, so your x's are with your dx and your y's are with your dy. Step two is integrate. So we learned about integration. We haven't taken an integral without the use of a calculator in a while, but those skills need to come back to you now. Here's an example question. Let's just do something very simple like this. So derivative of y with respect to x equals 2x over y. We are going to manipulate this, so rearrange it so that the x's are with dx and the y's are with dy. So just to note first, I hope by now you realize that I can't, if I rearrange this in such a way that I end up with this, something like that, this doesn't make sense. You can't have dy in the denominator. So that's not going to work for me. Here's the first thing I almost always do, is I multiply both sides by dx to move that to the other side. So now I have dy equals 2x over y times dx. So I'm partway there because I have my x's with my dx, but I have to move this guy to the other side. So I'm going to multiply both sides by y, and then I think I'll have it. So I have y dy equals 2x dx. Great. It is separated. X's are with dx, y's are with dy. It makes sense. Step 2 is to integrate. So just like derivatives, integral is an operation. So I can integrate both sides of this equation. Okay. Integrating y with respect to y, it gives me y squared over 2 equals, this is just going to be x squared because the 2 over 2 reduces. And don't forget your plus c. I'm only putting a plus c on one side of the equation. There's no reason to write plus c on both sides because c is just an arbitrary constant. It would be redundant to put it both places. So a lot of times you would be able to stop here. Sometimes they make you get y alone. So if that's the case, we can do that. I'm going to multiply everything by 2 and square root everything. And I'm going to remember that when I square root, I end up with 2 solutions. So I'm putting plus or minus on the outside of my solution. So this is called, when you have a plus c in your answer, any one of these, any version of it is called the general solution. I could give you the exact same question. Well, maybe I should write the question. I can give you the exact same question of dy dx equals 2x over y, and also give you a point that it goes through and say, hey, find the particular solution that also passes through the point 0, 1. So the process is the same. I'm still going to separate, and I get y dy and 2x dx, and I'm going to integrate both sides, and I'm going to get y squared over 2, and I'm going to get x squared plus c. But now I have a point I can plug in to evaluate what this plus c is. So this is an x value, this is a y value. I'm going to have 1 over 2 equals 0 plus c, so c is a half. So now my equation turns into the one particular curve, y squared over 2 equals x squared plus a half. And then I could keep going with getting y alone if they needed me to. Sometimes they need it, sometimes they don't. But this is called the particular solution. Remembering that a plus c can be anything, but if I solve for c, then I'm finding the one and only particular solution. So these only get difficult when you don't separate correctly, or when you don't remember how to integrate, which surely won't be a problem for you. Let's do one more. Let's do this one. I'm keeping these integrals simple because the purpose of this lesson is not to remind you how to integrate. It's to show you differential equations. So just know that tougher integrals can come at you. When I separate here, I'm going to multiply dx to the other side. I'm going to divide by y, and I'm going to end up with 1 over y dy equals dx. And I'm going to integrate both sides. And I'm going to remember the rule. This is y to the negative 1, right? So I can't add 1 and divide by the new because I'd be dividing by 0, and that's a problem. That's okay. I remember the rule, natural log absolute value equals, this would just be x plus c. All right, we're going to keep going. I want to get y alone because I'm nervous about your ability to clean up log equations. To get y alone, I have to get rid of the natural log. To get rid of a natural log, I have to do the inverse operation. The inverse of natural log is base e. So I'm going to raise both sides of this to base e. Here's a note for you if you are writing down common mistakes. You cannot base e separate terms. You base e an entire side of an equation and an entire side of an equation. So that makes these goodbye. It's still absolute value. We'll deal with that in a second. This is e to the x plus c. Okay, nobody is ever going to write this. You need to think about this as e to the x times e to the c. Remember, they have the same base, so we can add their powers, which means I can split them back up just as easily. E is a constant, c is a constant, which makes this whole thing just a constant. So instead of writing a constant to a constant, which feels unnecessary, a lot of books, a lot of places, a lot of, if you see this in like multiple choice answers, we'll just call it a. So what you really have here is absolute value of y equals a e to the x. And then to get rid of the absolute value, we just throw a plus or minus over here. And I don't know if it's plus or minus. Okay, so that would be the general solution. Let's have a discussion about what you were saying to me when you write all this stuff. This means slope, dy dx. This is a function value. So this differential equation says the slopes of my function at any point are always equal to the y value at that point. So the slopes of my function at any point are always equal to the function value itself. Well, yeah, it must be e to the x. The derivative of e to the x is e to the x. The derivative of that function is just that function again. That's what you have just said to me in this question. All right, kids, into Delta you go. Let me know if you need anything.